The previous stage, conceptual design, has resolved what the business stakeholders want from the system and what the key stakeholders think the system needs to be able to do in order to deliver that capability to the business. The key stakeholders have articulated their understanding of the system level requirements in order to explain what the system needs to be able to do, how well it needs to be able to do it, under what conditions it needs to perform, and what other systems are involved in its performance of those functions. Additionally, the key stakeholders have also decided on how the function and performance of the system will be proven by describing the verification approaches for each of those requirements. The stakeholders will have identified viable system-level solutions to their requirements and weighed up the pros and cons of each of those options. It's critical to remember that the pros and cons will include not only the solution's ability to meet function and performance requirements, but also other things like cost, schedule, risk, and life cycle issues such as sustainment and disposal costs, capability considerations such as training, personnel, and organisational issues. Based on this complex and interrelated set of considerations, the stakeholder group will have made a decision and chosen a preferred solution. If this solution is being provided by an external organisation, a contract will have been negotiated between the two organisations. To differentiate, we will refer to the organisation who needs a solution as the customer and the organisation providing the solution as a contractor. The contract can be thought of as a description of the respective responsibilities and allocation of risk between those two parties. If the solution is being provided by an in-house resource, systems engineering practice would still highly recommend that a contract-like agreement between the in-house customer and the in-house solution provider exists. This contract-like agreement will document the requirements for the solution and document the agreement between the in-house parties. Either way, once we've got that agreement sorted out, we have concluded the conceptual design with a review of our requirements and the proposed solution, just to confirm our readiness to commence the more detailed design activities. We're about to embark on a process that will see our logical solution, that is a thorough understanding of what we want to achieve, translated into a physical solution, that is a real and usable solution. It's important to note here that I'm not suggesting that the solution needs to be physical in the true sense of the word. A piece of software, for example, is not something that we can touch or weigh or feel, but it's definitely something that can provide us with a usable solution to a problem. In this module, we're going to continue to use the house example, so this will be a physical solution in the true sense of the word and in the systems engineering context. At the conclusion of the conceptual design phase, it's highly likely, it's probably essential actually, that the designers of the preferred solution would have at least a preliminary idea of what the proposed solution was going to look like. They'd have a pretty good idea about how the system will be broken down into system elements, or what we're going to call subsystems. They'll also have a pretty good idea at roughly how each of those elements will contribute to the overall solution and how those elements need to interact or interface with one another. For example, we'd expect the designers of our house to know that it will have an electrical subsystem and will require a plumbing and drainage subsystem. We'd also expect to know that the house would have bedrooms, living areas, a kitchen, bathrooms, and so on. We'd probably also expect at this stage to have draft drawings and plans available to show us the conceptual design of our house. The aim of preliminary design is to look in more detail at each of those subsystems and determine what each of those subsystems needs to be able to do in order to collectively satisfy our stakeholders, or in this case, the people who will end up owning and living in the finished product. To perform preliminary design, we perform a requirements analysis and allocation process, much like the one that we did during conceptual design. But we tend to start with an understanding of the subsystems as discussed above, and then look to understand what requirements each of those subsystems needs to meet in order for the system to achieve its requirements. We're going to end up with a hierarchy of requirements here. System requirements leading to subsystem requirements. Let's look at an example. Assume we have a requirement at the system level that promotes environmental friendliness of our design. It's highly likely that this system level requirement would lead directly to a requirement for rainwater to be collected and used within our house system. Logically, rainwater harvesting, storage and use would be allocated to the plumbing and drainage subsystem. The same subsystem level requirement may lead to the need to convert sunlight into electrical energy for storage and use in the house, or even for sale back to our energy company. This set of subsystem requirements would be allocated to the electrical subsystem and may lead to previously unknown requirements, such as the need to interface to the energy company in a particular way. As we're going through this process, we maintain traceability within the requirements hierarchy so that we always know where our requirements have come from. In systems engineering, people talk about forward traceability and backward traceability to give a feel for which direction within the hierarchy we're talking about. Forward traceability is from the system level requirements to the subsystem level requirements. By ensuring forward traceability exists, we're able to show our stakeholders that we've listened to all of their requirements and all of their requirements are being accounted for somewhere within our design. Forward traceability is very important when trying to deal with changing requirements. For example, let's use the previous example to illustrate this. If the stakeholders decided that environmental friendliness was no longer required, we would be able to trace that requirement to the rainwater harvesting requirements in the plumbing and drainage system and the equivalent electrical requirements in the electrical subsystem, and we'd be able to remove those requirements from our consideration. Backward traceability is used to show how particular subsystem requirements relate back to the system level requirements. Backward traceability helps us to show that all of our subsystem requirements are there for a reason. That is, they contribute somehow to the system level function and performance. This helps us avoid what is often called requirements creep, where our requirements progressively get more and more capable than they need to be. Although this sounds like a good thing, requirements creep progressively takes our system away from where it was intended to be. It can end up costing more than it needs to be and taking longer to realise. Also, when subsystems are competing with the same finite resources, requirements creep can actually cause some of the subsystems to exceed their requirements whilst others are left struggling. In these cases, we may end up with a system that exceeds some function and performance requirements whilst failing others. In systems engineering, we are interested in meeting all of our requirements, not exceeding some and failing others. An example might be the design of an air conditioner in a normal car. Let's say at the system level, or at the car level, we have a requirement to keep the whole occupant space cool, say to a temperature of 18 degrees, even when the outside temperature is 40 degrees. The system level requirement might even say that 18 degrees needs to be achieved within, say, 5 minutes of the temperature being activated. Naturally, this system level requirement will end up getting allocated to the air conditioning subsystem. Now, the guys doing the air conditioning are really keen guys and they've got some really good ideas. And they start calling the air conditioner a split zone air conditioner because they think the occupants might really want to be able to keep the front of the car at a different temperature from the back of the car. So their design concept includes essentially 2 small air conditioners instead of 1 big one. Their design therefore includes just a little bit of extra wiring, a little bit of extra plumbing, and a couple of extra computer controls associated with the split system. There's going to be a controller in the front and a controller in the back. Oh yeah, there's also got to be some additional sensors in the car now to take account of the fact that we need to be able to measure 2 temperatures, not 1. Sure, the split zone air conditioner weighs a little bit more than the equivalent single zone system with all that extra wiring and plumbing and so on. And it's a little bit bulkier when you take into account all those extras, and it uses a little bit more electrical power. But gee, you're getting a really good air conditioner, right? Sure, you're getting a really good air conditioner, but when you look back through traceability to the system level, the only thing that the system guys asked for was to keep the whole occupant space cool to 18 degrees, even when the outside temperature was 40 degrees. So where did this requirement for a split air conditioning system come from? It crept into the design at the subsystem level. People might say, yeah, but you ended up with a much better system than you asked for. No, you didn't. You ended up with a much better subsystem than you asked for, and it weighed more, used more electrical power, it occupied more physical space in the car. All of these things, when combined with all of the other subsystems, might end up resulting in a car that is too big, too heavy, underpowered, with lousy fuel efficiency. That is requirements creep. Backward traceability is important in protecting us from these sorts of situations. Backward traceability also helps us if we discover that one of our subsystems is not able to meet its requirements. We are then able to use traceability to find out what system level requirement might be at risk. Another task that we need to perform during this process is the identification of the interfaces that need to exist within our system and between our system and its external environment. Remember, these external systems are outside our boundary, but we still need to interface with them if we are going to be successful. For example, our plumbing and drainage subsystem in our house will need to receive an input from the domestic water supply and will need to provide an output to the domestic sewerage system. These are examples of external interfaces. We identified these during conceptual design. During preliminary design, we also need to identify internal interfaces. For example, we may need to designate the kitchen as a subsystem. The kitchen subsystem will need interfaces from the electrical subsystem and from the plumbing and drainage subsystem in order to perform its function as a kitchen. Interfaces will come in many shapes and sizes. For example, we might need to define physical interfaces like pipes and wires, electrical interfaces like voltage levels, hydraulic interfaces like water pressures, and electronic interfaces such as communication signals. These interface requirements are critical to us and will place additional constraint on our subsystems, so they are identified and defined during preliminary design so that we can take account of them when we perform detailed design.
If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.